When we look at a star, all we can directly see is its glowing outer surface. But beneath that surface is an enormous natural machine. Matter is being compressed by gravity. Energy is moving through layers of superheated plasma. Atomic nuclei are combining deep inside the core. And every second, that hidden process produces enough energy to illuminate an entire planetary system. So, what would we find if we could somehow travel inside a star? In this video, we are going from the center of a star all the way to the light that finally escapes into space. A star is not simply a giant ball of fire. Fire is a chemical reaction involving materials such as fuel and oxygen. Stars work very differently. Most stars are enormous spheres of plasma held together by their own gravity. Plasma is a state of matter in which atoms become so energetic that electrons separate from their nuclei. This then creates a mixture of charged particles that can conduct electricity and interact strongly with magnetic fields. For this explanation, we are going to use the Sun as our main example. The exact details differ between stars, especially depending on their mass and age, but the Sun gives us a very useful picture of how an ordinary main sequence of a star actually works. Before entering the star, we need to understand why it does not simply collapse or explode. A star exists because of a balance between two opposing effects: gravity, which pulls all of the star's matter inward. Every particle attracts every other particle, and because a star contains an enormous amount of mass, that inward gravitational pull is extremely powerful. But the hot material inside the star also creates pressure that pushes outward. Energy is released from the center, which heats the surrounding plasma. That hot plasma moves rapidly and produces pressure against the weight of the material above it. So when the inward force of gravity is balanced by the outward pressure of the hot gas and radiation, the star remains stable. And this condition is then called hydrostatic equilibrium. It does not mean the star is inactive. It just means that the competing effects are balanced closely enough for the star to maintain its overall shape. If the balance changes, the star changes too. That will become extremely important later in its life. At the center of the Sun is the core, and this region occupies only part of the Sun's radius, but it is where almost all of the Sun's energy is produced. Gravity compresses the material in the core so intensely that the temperature reaches roughly 15 million degrees Celsius, and this amount of pressure is quite enormous. Under these conditions, hydrogen nuclei move at extremely high speeds. Most of the time, positively charged nuclei repel one another, but occasionally they approach closely enough for the strong nuclear force to bind them together. Through a chain of reactions, hydrogen is gradually converted into helium, and this process is called nuclear fusion. The mass of the final helium nucleus is slightly smaller than the combined mass of the original hydrogen nuclei. That missing mass has not disappeared. It just has been converted into energy according to Einstein's equation, which is E equals mc squared. Because the speed of light squared is an extremely large number, a small amount of mass can produce a tremendous amount of energy. The Sun converts hundreds of millions of tons of hydrogen into helium every second. Only a small fraction of that mass becomes energy, but that is still enough to power the Sun continuously. It may sound as though the Sun contains one continuous nuclear explosion, but fusion inside the Sun is not the same as an uncontrolled explosion. The Sun's energy production is regulated naturally. If the core becomes slightly hotter, the outward pressure increases. The core expands a little, which reduces its temperature and slows the fusion reactions. If the core cools, gravity compresses it more strongly. That compression raises the temperature and allows fusion to increase again. This feedback helps keep the sun stable over extremely long periods. The sun has been shining for billions of years and is expected to remain in its current main sequence stage for billions more. The energy created in the core, though, now has to escape. Immediately outside the core is the radiative zone. And here, energy is transported mainly through radiation. But this does not mean that a particle of light travels directly from the center of the sun to the surface. The plasma is extremely dense. Photons are repeatedly absorbed, scattered, and re-emitted by particles in the sun. A photon may travel only a very short distance before interacting with matter again. Its direction can change countless times. This creates a slow, random journey outward. The energy produced in the core may take an extremely long time to move through the dense interior before eventually reaching the outer layers. During that journey though, the energy is repeatedly redistributed and transformed. The visible sunlight reaching Earth is therefore not simply, a collection of unchanged photons traveling directly from the original fusion reactions. It is the result of energy gradually making its way through the star. Closer to the sun's surface, radiation becomes less effective at transporting energy. This is where the convection zone begins. In this region, energy is carried by the movement of plasma. Hot plasma rises toward the surface. As it rises, it releases energy, cools, and becomes denser. The cooler material then sinks, where it can be heated again. This then creates enormous circulating currents. You may recognize a similar process in a pot of heated water. Although the conditions inside the sun are vastly more extreme, at the visible surface, these convection currents create a pattern known as granulation. Each bright cell represents hotter material rising. The darker boundaries are regions where cooler plasma is sinking. So when we observe the textured surface of the sun, we are seeing evidence of the movement taking place beneath it. The layer we usually think of as the surface of the sun is what we call the photosphere. The sun does not have a solid surface that someone could dare to stand on. The photosphere is simply the region where the plasma becomes transparent enough for light to escape freely into space. Its temperature is approximately 5,500 degrees Celsius. Although that is extremely hot, it is much more cooler than the core. The photosphere is where most of the visible sunlight we receive originates. From there, light takes a little over 8 minutes to travel from the sun to Earth. That just means every time you see sunlight, you're seeing the final stage of an energy journey that began deep inside the sun. The sun is not perfectly calm. Because the sun is made of plasma, its movement can generate complex magnetic fields. Different parts of the sun also rotate at different rates. The equatorial region rotates faster than regions closer to the poles. This movement stretches and twists the sun's magnetic field. Sunspots form where concentrated magnetic fields interfere with the normal movement of hot plasma. Because less heat reaches these regions, they appear darker than the surrounding photosphere. They are extremely hot. They only look dark because the surrounding material is even hotter and brighter. Twisted magnetic fields can also produce solar flares and coronal mass ejections. These events can send radiation and charged particles into space, sometimes affecting satellites, communications, as well as power systems near Earth. Above the photosphere are the sun's atmosphere-like outer layers. The first is the chromosphere, a relatively thin region that can appear reddish during certain observations. Beyond that is the corona. The corona extends millions of kilometers into space and is visible clearly during a total solar eclipse. One of the most interesting mysteries is that the corona is much hotter than the visible surface below it. The photosphere is around 5,500 degrees Celsius, while parts of the corona reach temperatures of more than 1,000,000 degrees. The precise mechanisms heating the corona are still an active area of research. Magnetic activity, waves within the plasma, and small-scale energy release events are all important parts of the explanation. This is a useful reminder that even our own star still contains unanswered scientific questions. We cannot physically travel into the sun, so how do scientists know what is happening inside it? Well, one method is spectroscopy. When sunlight is separated into its component wavelengths, dark and bright lines appear in the spectrum. These lines reveal which chemical elements are interacting with the light. Spectroscopy allows astronomers to determine the sun's composition, temperature, and motion. Another method is helioseismology. This is when the sun vibrates. Waves move through its interior and cause subtle oscillations at the surface. By measuring those oscillations, scientists can infer information about the density, temperature, and movement of material below the surface. It is similar in principle to using seismic waves from earthquakes to study the inside of Earth. Scientists also detect neutrinos produced during fusion reactions in the sun's core. These particles interact very weakly with matter, allowing many of them to travel directly out of the sun. Detecting solar neutrinos gives us direct evidence that nuclear reactions are occurring in the core. So, our model of the sun does not come from imagination alone. It is supported by several independent forms of evidence. A star is a balance between gravity and pressure. At its center, hydrogen nuclei fuse to form helium and release energy. That energy moves through the radiative zone, then through the convection zone before escaping from the photosphere as light. Above the surface, magnetic fields shape sunspots, flares, and the enormous outer corona. And although we cannot enter a star, spectroscopy, solar vibrations, and neutrinos allow us to investigate what is happening inside. The next time you look at the sun or any star in the night sky, you are not simply looking at a point of light. You are looking at an enormous structure governed by gravity, plasma, nuclear physics, and billions of years of stellar evolution. And this is only the beginning of what stars can teach us. This is the first video in The Universe Explained, where we explore astronomy and astrophysics one question at a time. Subscribe to follow the series and my journey from astronomy student to independent scientist. In the next star-related video, we can investigate how astronomers use starlight to discover what stars are made of.